Okay, welcome to the Chapter 15 video for you guys today, Geologic Structures. Now, what we're talking about in this chapter is basically a subset of geology that we call structural geology. This is really about the architecture of the Earth's crust. Generally speaking, the Earth is not static in nature, and therefore you have a lot of deformation or changes to the nature of the rock in terms of its original structure. So basically what we're going to be looking at is how this deformation happens, what sort of features does this deformation create. Now, one of the things that we have to really set up first and foremost is to define deformation. This is a rather generic term, general term, but for our purposes, it's going to relate to all the changes in the original form and or size of a rock body. So if we change the size of the body, if we change the shape of the body, that is deformation. Now, the vast majority of crustal deformation occurs along the plate boundaries, especially the spreading boundaries and the collision boundaries. So what does deformation involve? Well, first and foremost, like many things in physics, it involves a force. So what's a force? Well, it's a pen, right? Right. All right, marker. Force acting on it. Is there a force acting on it? Well, technically there's a couple of forces acting on it. There is the force of gravity pulling it down. There is the force in this chain, which is going into my hand, which is counteracting gravity. If I let go, gravity acts on it alone and it falls. So, most simply stated, a force is something which changes the nature of motion of an object. So if this object is at rest, it's going to stay at rest unless acted upon by an outside force. If this object is in motion, it should stay in motion unless acted upon by an outside force. At rest is easy. If it was like that and I come around and hit it, that's it. That shows it. Motion, showing it staying in motion is a little harder because there are forces that will act on it. If I throw it, there's going to be gravity that acts on it. There's going to be friction that acts on it. I'd have to throw it incredibly fast and incredibly hard for it to demonstrate that. But generally speaking, that's what a force is. It's something that changes the nature of an object's motion. Another term we need to understand is going to be stress. So what do we mean by stress? For the purposes of physical geology, what we're really going to be meaning is similar to pressure. It's a force applied to a given area. So when we talked about metamorphic rocks, we talked about differential stress or differential pressure. So that was the force acting over a given area. And if you remember from our talk about metamorphic rocks, there are confining pressures or confining stress, which is equal in every single direction, and as a result, it will usually cause something to shrink uniformly. Again, the example I used for that was the sunken head, or no, sunken head, the styrofoam head that they took down to the Titanic as part of the special when they found the Titanic. Those styrofoam wig heads that are full-size human-shaped heads of styrofoam, left it in a container outside of the submarine and took it down to the Titanic, brought it back up. When they did, it was about yay big. It had shrunk, but uniformly, perfectly. The other type of strain or stress that we can see is differential stress, and this is going to be the stress that's applied in different directions. Okay, now, because it's unequal, that means we can have a couple of different types of differential stress. The first one of these is going to be compressional stress. So compressional stress is squeezing something in, like that. So I'm pushing the sides in, and the material is responding in whatever way it deems most appropriate to that stress and how it's being put in. Okay, so that is a compressional stress. Then there is a tensional stress, and I'll demonstrate tensional stress in a little bit different way. Tensional stress is a pulling apart. So I have to use compression to put the lid back on, tension to pull it apart. Okay, this helps you explain why certain structures are built the way they are. For example, when we build a bridge out of concrete, one of the things we put into it is rebar. Why do we put rebar into concrete? Well, it's very simple. Concrete is very strong under compression, very weak under tension. Rebar, on the other hand, is strong under tension but weak under compression. So we're using the materials to complement each other and to strengthen what needs to be strengthened in the proper locations and areas and provide that additional ability to withstand the stresses involved. Now, differential stresses do not have to work in the same directional plane at the same time. They can be offset. When you get an offset stress, that kind of creates a situation like this. Let's see if this will demonstrate, where you get one part moving in a different direction. It might be easier if I do it this way. There we go. So if I press here, you get that differential. So the top is being pushed one way, the bottom is being pushed the other way, and it creates this rotational deformation. Okay? So we can see this in the rocks, and we can look at the rocks and study the rocks and get into the whole thing about where the stresses were coming from, how much stress, how the stressing was timing and whatnot. We don't need to do that for here. What I need you to remember is compressional stress, pushing in, tensional stress, pulling apart, differential stress or shear, which ends up being a rotation of some sort. Okay? Now, the final term that we need to understand in this is strain. Strain is a very specific term in geology, especially in material science. What we're really talking about is the point at which we make an irreversible change in the shape or size of a rock body when we apply a stress to it. So, as an example, I'm going to take a business card because I don't want to destroy anything else. I take the business card and I bend it. And it pretty much goes back to almost the way it was. This is what we call elastic deformation. Okay? I'm not bending the card beyond a point where it cannot recover. Okay? So the same thing with a pencil. You can bend a pencil. This is a mechanical pencil, but still, you should be able to see that I'm bending it. But I let go, it goes back to being straight. Okay? Strain occurs when we take it beyond the point where it's going to be able to recover. So if I let go there, I've kind of strained this material. Now, this material being so flexible, I can kind of fix it too. But it still has a degree of bend in there to it. But that's what strain is. Strain is going beyond the strength of the material to the point where you're irrevocably changing the shape of the material. Okay? So, how do rocks deform? Well, they're going to deform in one of three ways. They can fold, which is this demonstration. They can flow, which is I wish I had some here right now. I just realized that what little silly putty I have is actually locked up in the college. But if you had clay, also the same difference. If you've ever played with modeling clay or silly putty, you might understand that you can squeeze it and it will flow out. You can put pressure on it and it will ooze. With silly putty, you can roll it into a ball, sit it on a surface, walk away, come back, and it will flatten out. So we can see that materials can flow over time. And then the third way that they can deform is through fracture. Okay, so fold, flow, or fracture are the types of deformation we can see. So when we look at the types of deformation, we get back to the idea of elastic deformation first and foremost. Elastic deformation is simply the material is deforming, but will return almost back to its original size and shape when the stress is removed. This plays a major role, as we will see later on, in earthquakes. When you have an earthquake set up, that is through elastic deformation and energy release because of the release of that elastic strain. Now, once you pass what we call the elastic limit, or the material strength of it, the material is either going to flow, ductile deformation, or it's going to fracture, brittle deformation. So let's look at the different factors that play a role in this, and we're going to keep a couple of them in mind. The most important one to me is going to be the last one we talk about, but we're going to go through all four of these. So, first and foremost, what influences the strength of the material? Let's start with its temperature. Okay, if you've ever taken a spoon, not a plastic spoon, but a metal spoon, and bent it back and forth, you ever notice how over time it gets easier to bend, and the point where you're bending it is getting hot? Well, that's because temperature actually makes it easier for things to be deformed. The warmer something is, the more likely it is to deform. The warmer it is, the more likely it is to undergo ductile deformation. So hotter things deform ductily. If you've ever watched the show Forged in Fire, that's a lot of what they're doing. If you've ever seen a blacksmith work, that's what they're doing, is they're heating the metal up and they're moving the metal ductily by hitting it with a hammer. Okay? The next step is confining pressure. How much pressure is the material under? Let's see, I think it's in this other book. Pressure really can play a role in how strong materials can be. Let's see if I can find this here. As the confining pressure increases, the strength of the material will also increase. Let's see, here we go. Hopefully they didn't remove it from this book. Looks like they did. Used to have a display of cylinders of rock. One of the ways they test the strength of material is by taking cylinders of rock, putting it in for all intents and purposes, a giant press, and pressing it together and seeing at what point does it fracture. It's a strength test, basically. Yeah, they don't have it. One of the things you can see is that depending on how you confine the material, how strong the confining pressure is, the less deformation you get. Rock that has no confining pressure on it, when you put enough pressure on it to break the rock, it basically, for all intents and purposes, will explode. Pieces will go flying out explosively. As you increase the pressure on it, the pieces don't move as much, and you don't see as large of fractures in it. So with large confining pressures, you're tending to see more of a ductile or a flowing type of deformation. Now, of course, the third type of factor playing a role in the strength of a rock is going to be the rock type. Different types of rock have different strengths. Sandstone tends to be a little bit stronger than certain types of limestone, but certain types of limestone can also be stronger than sandstone. Really depends on the nature of the rock itself. Granite, however, is much stronger than any sedimentary rock tends to be. Quartzite tends to be much stronger than a lot of rocks. So really depends on the type of rock you're dealing with. The final factor is time. Like all things in geology, time matters. Time makes all things possible, as they say. If I take this card and I bend it fairly slowly, I can get it to touch. I can bring it back, and not much of a bend in it. Okay? Straighten it out. If I bend it quickly, oops, got a much stronger fold in it. I've actually physically damaged it. Okay. If you've ever played with silly putty, the same thing. You put the silly putty down and push on it, it will spread out. But if I take a hammer and hit it, it will shatter like rock or glass. So the amount of time really matters. If I take a piece of glass, support it on its two edges, and then put a weight in the middle of it slowly and let that weight sit there over a period of time, it will bend the glass. If I put the same amount of pressure that weight did over a same amount of time, over a different amount of time, shorter piece of time, I'll break the glass. So time can really matter. How fast are these forces acting? The faster the forces act, the more likely we are to see a brittle deformation or a fracture than we are going to be seeing a ductile deformation or a fold or a flow. So, what about geologic structures? How in the world do we figure out what a structure is? Well, and I should have grabbed this beforehand. Let's see. Is it over here? Nope, don't see it. I don't know where my Brunton Compass is. I thought I knew where it was. In geology, one of the things that we use is something called a Brunton Compass. It's a specific compass designed for taking measurements of geologic structures. So when we do this, part of the issue that we get is we're really limited. We only can see what's at the surface of the earth, where we have rocks exposed. So if we don't have rocks exposed, we're kind of a little bit of a disadvantage. Now, road cuts help us out, by building roads and building the interstates. We cut through hills, we cut through mountains. We expose some of the structures that way. We can also see stuff now with advances in aerial photography, satellite imagery. Global positioning satellites really are adding to this field right now. One of the things they do is put GPS units out and can actually measure how the surface of the earth is changing minutely over time. That's how we were able to see that Mount Everest is still rising up at a certain rate, how we can actually watch in some areas of California the ground deformation that's occurring because of the strain building up in certain fault lines. So really a lot of interesting science now happening with GPS materials. But our basic tool is going to be the Brunton Compass, no matter what. So a Brunton Compass is a compass that is set up for looking at two different measurements we normally use in geology. There it is. I can show you a Brunton Compass, kind of, sort of, not really. In your lab book, page 106, bottom is a diagram I've made of a Brunton Compass. Okay, so Brunton Compass has your normal compass on it. It has a bullseye level, so you can get it nice and flat. It also has a what we call a clinometer level, a bar level basically, and this toggle down here, which allows us to measure angles. So what we're going to measure with this are two features of rocks that we have developed to be able to look at the structures. One is called strike, the other is called dip. The best way to demonstrate strike is, imagine, if you will, a rock unit that's not horizontal. So let's say this is a rock unit that's not horizontal. Now imagine a horizontal plane intersecting that rock unit. The intersection of any two planes is considered a line. The strike is the measurement of that line. So the easiest way to think of it is strike is going to be the compass direction of a line produced by intersecting a horizontal plane with the inclined rock. Generally speaking, we will express that as an angle relative to north. We're in the northern hemisphere, we're north-centric. So it would be like 10 degrees 10 degrees or east 10 degrees or north 10 degrees east. So if I was to measure 340 degrees, that would actually be north 20 degrees west. And when we do the lab on this, you'll actually see this layout and actually work on some of these conversions. But generally speaking, there's two ways that we do strike and dip. Based on the circle 360 degrees, you can either do it in quadrants northeast, southeast, southwest, northwest, or we can where each one goes from 0 to 90, where 90 is going to be the east or 90 is going to be west, and then we're measuring from the south or from the north. And then there's the 360, which is just a 360 degree measurement. The other thing that we measure is dip. Dip is the angle below the horizontal of the material. So if the material is like this, then the angle between the horizontal plane and the face of this material would be the dip. Dip only goes to 90 degrees. So it's either 90 or 0 or somewhere in between. Okay. Again, when we do Lab 9, hopefully this will make a little more sense. Lab 10 will also talk about this. Lab 10, you would actually make a measurement like this. I'm still working on Lab 10. I'm still working on Lab 8, so we'll get those to you here shortly. So let's talk about actual features of deformation that we can see. And this is going to be fold. The first one we're going to start out with are folds. Folds are a very simple one. What's a fold? It's real simple. The rock is bent in one way or the other. Okay? So, generally speaking, these undulations are what we call folds. The vast majority of folds, if not all of them, are compressional in nature. So what's happening is the ground is being squeezed, or the crust is being squeezed together, and it's getting shorter. So points are getting closer together somehow, some way. Now, there are a couple of different parts to a fold that you should know. And we can draw those out. All right, so there's a fold, and what we have with this fold is we're going to have the limbs, which are the sides. So the sides are the limbs, okay? This line here is going to be the axis. The axis is the maximum is the point of maximum curvature in the layer. That you can also think of that if you have multiple layers and you run through it, you can get what we call the axial plane. It's an imaginary surface that divides a fold symmetrically as possible in half. Okay. Now, generally speaking, folds have two different orientations that we consider in general. One is if the axis is horizontal, it's just a horizontal fold, or it's parallel to the surface. If the axis is at an angle to the horizontal, we call that a plunging or an inclined fold. So we use the term plunging for it. So, what are some common types of folds? Well, thankfully, there's only really 3 folds that we have to really, really worry about, okay, in general. First, what I've drawn here is called an anticline. Basically, it's an upward folded arch. So the rocks fold upwards, okay? Now, if I was to cut through this, what that means is that the material in the center of the fold is going to be older than the material on the outside of the fold. So if I cut through this, the materials are older underneath. Again, with the idea of superposition, where the layers underneath are older than the layers on top. Okay? The other thing you can do with this is if we look at strike and dip, we can draw strike and dip with a symbol that kind of looks like a T. like that. This would be our strike and dip symbol. Okay? If we draw that on both sides of the fold, we see that in anticlines, the folds, the limbs are going to be dipping away from the center of the fold. Okay, so we can tell that by that way also. And also we tend to, usually speaking, when you're dealing with inclined rocks, they typically dip away from the old and towards younger, is another good rule of thumb you can use. So a different type of fold that's very related to the anticline is the syncline. So again, the syncline would be a downward fold or a trough of rock. So again, this would be the limb, and the axis, like that. So with these two folds, it's very simple. As long as the axis is horizontal, we just call it an anticline or a syncline. If the axis is at an angle, we call it a plunging syncline or plunging anticline. Now we can actually look at the layers in the rock, and you're going to see this in Lab 9, and because these will make specific patterns. If I was to look at this as a map view and look at what pattern can a syncline or anticline create, one of the things I'll note is this. Okay, so if I'm dealing with a syncline or an anticline, one of the things I can do is when I do these block diagrams, I can number them so we can see how things are behaving with each other. And if I draw these with a strike and dip symbol on them, that might help also. So while I get these drawn up real quick, okay. So I've drawn a couple of displays on how this would actually look on a map. So for a regular anticline, if we were to plane it off, we would see something that looks like this, where the oldest layer is in the center, younger layers go out to the sides, and everything is dipping away from the center out towards the younger materials. If that was actually tilted, we would see something more like this, where it closes or it opens up towards the younger material. So you would see these bends that would then open up towards, I'm sorry, not younger, towards the older material. So the older material would be closer in. Whereas on a syncline, it's the opposite. So in a syncline, we see everything pointing in towards the bottom or towards the youngest material. And in a syncline, it opens up towards the youngest if it's plunging. Okay, so we're going to look at these again in Lab 9, and you'll be trying to make that interpretation. Now, this is where being able to visualize things in 3 dimensions can help you if you have that ability. If you don't, by no means should you feel embarrassed in doing the following. Take a piece of paper, take a pad of paper, I don't care, and visualize, bend it, and visualize what's happening as you're doing these things. This is an easy way to do it. If you can visualize that in your head, no problem. If you can't, use a tool. Use a piece of paper. Doesn't hurt you to do it. If you're taking a test, use the test. Okay? Now, there is one other type of fold. I said there were 3. We've covered 2. The anticline and syncline. The other one is what we call a monocline. Now, a monocline is a little bit different. It's a stair-step fold. Generally speaking, monoclines are probably expressions of incomplete faults. So what we would have is something like this. And I'm going to draw it a little exaggerated. What we think happens with a monocline is we have a fault of some sort underneath it. It activates a little bit, but the overlying layers bend, they don't break. So you get this stair step of a fold. One side is up, the other side is down, and you get a ramp in between, but it doesn't break, and there is no corresponding down on the other side. So that's what we call a monocline. Now, technically speaking, those are all the folds that we need. However, we can express other shapes by interacting those folds together. So if we cross-lattice 2 anticlines together, we're going to create a upward lifting circular structure, or somewhat elongated circular ovaloid structure that we call a dome. If we do it with 2 synclines, we would get a basin. So a dome, the oldest material is in the center. A basin, the youngest material is in the center. One of the things to keep in mind is that folds are related. Generally speaking, it's rather unusual to see an anticline or a syncline off by itself with nothing else around it. Generally speaking, you tend to see anticlines leading into synclines and synclines leading into anticlines. Okay? So, the next type of deformation is going to be the brittle side of the equation. What we've talked about so far was the ductile deformation, the stuff that's slow, happens over time, doesn't break the rocks. And so this is what breaks the rocks are faults. So a fault is a break in the rock, a fracture, but it's a very specific one. If it's just a fracture in the rock and nothing has moved, we call that a joint. But if the fracture has moved, and it's measurably moved, then we call that a fault. So we have to look at this in the way of, was there movement, or what we call displacement. Sudden movements along faults are what we call earthquakes. Now, when a fault happens, we can classify that based on the relative motion in the fault system. So, did the movement go vertical? Did it go horizontal? Or obliquely, which is a combination of both? Okay? For the purposes of this course, I'm only going to just mention oblique faults can happen. We're not going to go into them. Okay? They're a little bit too complex for this course. So, let's look at the faults based on the types of motion. Let's go first with vertical motions. Okay, so the motion across the fault is going to be vertically oriented. Now, when we do this, the way that motion occurs is going to determine the type of fault we're dealing with. So, let's work first with what we call normal faults. A normal fault is one where we had motion like this. Okay? Now, we need some terminology to help us understand the parts of the fault, so we're going to put a mine shaft in here, kind of like our field trip. There we go, got our mine shaft. Need a miner in there. Just for the sake of it, let's make Oscar our miner. So Oscar's our miner. He's in the mine shaft. We need to be able to come up with some terminology for the parts of the fault that he's looking at. He's standing on this part, right? So let's give this an easy name to remember. It's the footwall. His feet are on it, right? This part up here, well, we can give that one of two names. He can hit his head on it, so we can call it the head wall. Especially if I can spell. Or he can hang stuff on it. So it's the hanging wall. Either or will work for this purposes. But the hanging wall is going to be the rock that is above the fault, and the footwall is going to be the rock that is below the fault. So this is what we would call a dip-slip fault. In other words, the slippage is going to be along the dip of the faulting plane. So if we have this, remember a moment ago we said the strike is that orientation of the line that is created by the horizontal plane intersecting the inclined plane, and the dip is the actual vertical or is the angle below the horizontal. So we're doing the stuff along the dip. So hence we call it a dip-slip fault. Dip-slip faults have two primary types. Technically there's a third subtype. We'll get to that in just a moment. This one I've drawn is what's called a normal fault. In a normal fault, the hanging block or hanging wall moves down relative to the footwall. So if we were to put arrows on here that denote the motion that took place, we would see the motion looks like that. So the hanging wall went down, the footwall went up. This is produced by tension. So this is where the ground is being pulled apart. So it's a tensional fault. Normal faults are relatively only formed where you have tension occurring. Now, generally speaking, most normal faults have relatively small amounts of displacement, usually a meter or so in size. However, there are some normal faults that are known to have as much as 30 meters of displacement on them. So there can be large-scale ones, usually associated with block fault mountains like we find around us here in the Basin and Range, or the Grand Tetons or the Sierra Nevada of California. Generally speaking, this is very prevalent in areas where we see plate spreading or the extension of the crust. So the Basin and Range is thought to be in part a failed continental rift, and therefore that helps explain why we see a lot of normal faults within the area. We can also see these in those areas where I used the term before, Horst and Graben, where what you see is like this. In certain types of spreading centers, let's get this so you guys can see it. We get this extension where we have all these normal faults that are extending the crust. The up-thrown blocks are the Horst, the down-thrown blocks are the Grabens. Okay, now that's tension. Tension basically doesn't form any folds, and it only forms normal faults. What about compression? Well, if we do compression with a dip fault, a dip-slip fault, we get a completely different story. We get a reverse fault. And again, I think I've said this multiple times, we're not exactly unique in the way we name things. I mean, we could have called it George, I guess, I don't know. In a reverse fault, it's the reverse. What we see is the hanging wall has moved up relative to the footwall. Now, typically speaking, you don't see what I've drawn here often. And there's a reason for it. This material above the fault above the top of the fault of the ground here is going to be relatively unstable, and it will collapse fairly quickly gravitationally. So you don't usually see something that looks this pristine unless you're out there right after a movement, and the movement wasn't that big, only a few feet. But this would be a reverse fault. Now, there's a special type of a reverse fault called a thrust fault. I really don't like some of the way that some people describe these in terms of, oh, it's a reverse fault if it's more than 45, it's a thrust fault if it's less than 45. Thrust fault's not less than 45 degrees. It's a lot shallower than that, because a thrust fault, it really means that you're thrusting material up and over. So let me draw out a thrust fault for you. I'm going to do this with a little more detail in it than I've drawn the other ones before. Okay, you know what? I'm going to add a third color in here, just a second color, I should say, so it makes it easier to see. Just think, whether I'm doing this here in the video or in the classroom, you'd be seeing me do the same thing. Just sitting there with my back to you drawing. All right, hopefully this will make sense. So a thrust fault is a very low angle reverse fault where the material is literally pushed up and over. You get a thickening of the crust. You can actually see things repeating. So you can end up with something where, like, you're looking in this layer here and you see something like the sea scorpions, the Eurypterids. And this layer here has dinosaurs in it. And, well, dinosaurs and Eurypterids didn't live together, and dinosaurs came after Eurypterids. So you get this weird change in the fossil layers. So, but that would be a thrust fault. Thrust faults can actually be very, very low angle. I don't like the term 45 degrees. I usually, for me, thrust faults are a lot lower of an angle than 45 degrees. So that's a place where I disagree with some of the authors that are out there. But basically, they greatly accommodate crustal shortening and really, really, really occur in areas with very strong compressional forces. Not uncommon to see thrust faults that are very low angle. There's actually one in the Huachuca Mountains that's called the crestline thrust. The angle on it is about 1 degree above the horizontal. 1 degree. That's a very tiny angle for that thrust to have occurred at, but it's there. Okay, so that's the dip-slip faults. So we have a normal fault, reverse fault, and if the reverse fault is a low enough angle, it's a thrust fault. All right. Next up is the strike-slip faults. Strike-slip faults have horizontal motion on them. Most strike-slip faults are actually the third boundary of plate tectonics. So remember, we have the boundary where we have collision happening. We have the boundary where expansion is happening. Then we have the boundary where they're just passing by each other, or a transform boundary. Transform boundaries are literally the boundaries between two plates moving past each other without any vertical motion. So, the most famous transform boundary in the world is one you know. We call it the San Andreas Fault. If you were to go and stand with 1 foot on one side of the San Andreas Fault and 1 foot on the other side, 1 foot would be on the North American plate, 1 foot would be on the Pacific plate. The foot that's on the Pacific plate is trying to go north-northwesterly. This foot on the American plate, the North American plate, is trying to go south-southeasterly. So you have that motion. Generally speaking, when it comes to this type of fault, we say that it's either a right lateral or a left lateral. It's very, very simple to illustrate these and determine how we do it. It's by looking across the fault. Because no matter how you look across the fault, the directionality is not going to change. So, in a right lateral fault or a left lateral fault, we would see the following. And again, I'm going to draw this a little bit exaggerated. But this is to illustrate the point. And we'll throw a stream in there for good measure. Okay, that should do it. So, in these examples I've drawn up, map examples, the T's with the dotted lines or dashed lines connecting them, think of that as being power poles. So you have the T power pole with the transmission lines connecting it. The blue line with 3 dots, blue line, 3 dots, is an intermittent stream. We've already talked about that once before. So, when you stand on one side of the fault and look across, the fault gets its name based on the direction things moved. So in this thing, the other side, everything is moved to the right. Therefore, it's a right lateral fault. This one, everything moved to the left. It's a left lateral fault. If I turn it upside down, it still moved left. Doesn't matter which side I look at. Everything moved to the left relative to the side I am on. Okay? So that is the types of strike-slip faults. Again, they're like this. So, if anybody tells you that California is going to fall off into the ocean, you know the answer now is no, it is not. It's a lateral fault. That means it's moving like this. It's not. There's no vertical involved. It's not going to fall off into the ocean. Okay, that's why that movie about a mega tsunami hitting California came out a couple of years ago. Total, utter BS. It's not going to come from a magnitude whatever earthquake on the San Andreas Fault. That has to happen because Hawaii collapses. We can talk mega tsunami when we talk about earthquakes later. All right, let's see. And that just leaves us with the idea of joints. Again, I've already mentioned joints, where joints are fractures in the rock, but there's been no displacement. There's different types of joints that can occur. There's columnar jointing, which occurs in igneous rocks that cool down. They create these really cool hexagonal fractures. But joints are very significant to us because, one, they demonstrate stresses that are happening within the rocks that may not be great enough yet to cause full deformation of faults. They can tell us where we're going to expect to experience higher rates of chemical weathering, or they can be places where water ends up depositing certain materials. And also, finally, it's an area where we know that there's going to be a significant risk to human construction projects because something is happening to cause the rock to break up. So that should do it. I'm going to work on trying to get Lab 8 ready for you guys to go, and then I'll do a brief introduction video for Lab 9. And I'll talk to you guys on Monday.